Swayam Prabha. Digital India. Educated India.
So let's look at some advanced technologies and let's try to put intelligence into the networks. Right now, all the network did was work as a conduit, a very high speed and low latency conduit between compute elements. But we want to look at it now from an element which can do some more intelligence. Okay. So what do I mean by intelligent networks? Let's look at a simple, typical high performance computing operation, okay, or an AI operation. Why are we making this cluster? Why are we connecting all these computes together? So that we can run a very large single job by dividing it into multiple compute elements. When you do that, let's say you are doing a simple matrix vector multiplication, right? Any application which is trying to solve a partial differential equation will break down into a matrix vector multiplication or a matrix sparse vector multiplication. If it is a very large problem, it will be a very large matrix which will not fit into a single system. And obviously, you need to break it down and send it across to multiple systems. When you have sent it to multiple systems, they will all compute their portion. Okay? After they have computed their portion, they will try to exchange the data to each other, or they will try to send their results to somewhere, right? So there are I would say operations in which you would distribute data and then you would collect data, one to many and many to one. These kind of operations in networking domain are called collective operations, and it is required for every, even in iterative solvers, right? You do one iteration and then you will calculate a new weight, and you will do another iteration and then again calculate a new weight, and so on. Let's say everybody is, one big job was distributed amongst 100 servers and everybody got their job, and now they will do their job and they will send out their results to a master processee which will collate the result, get a new weight or get a new answer, and then send across more data to the other processing element. And this entire cycle will keep on repeating till your iterative process converges into a particular solution, or till the residual error is within the acceptable limits. So every scientific application and every AI and machine learning application also does this kind of communication. Now you can see, okay, one question was, what is a fat tree topology? A fat tree topology is nothing but, so as I said, if you wanted to connect 100 computers and I had a switch which had only 400 ports, and let's say I wanted to connect, I had a switch of 40 ports and I wanted to connect 400 servers. How would I do that? I will take lots of switches. I will, to every switch, I will connect maybe 20 servers, and I will uplink the switch to another layer of switches, so that now I form a two-layer topology where I have 20 ports connecting to servers and 20 ports uplinking to 20 different switches. Like that, I have a second switch as well, which has got 20 ports downlinking to servers, 20 ports connecting to again different switches. This whole thing forms a fat tree network. The way I have connected over here in a two-level distributed architecture, it's a fat tree network. Okay. If I have to cover topologies, it's a full session on its own. So let's not go there. But I just showed a simple fat tree topology to make a 400 node cluster. Now the problem is, when I'm running a job where I have a master process which needs to collect after every maybe 10 microseconds or 100 microseconds, it needs to collect data from everybody else. This data collection is, the master process is running on one particular server connected to one switch. Okay? Because master, as the name implies, can only be one, and all the slave processes needs to send data back to the master. So master will collect data from slave number 1, it will connect from slave number 2, from 3, and so on and so forth. It can collect only one by one. Why? Because master has a single link to the switch. You cannot say that, hey, why don't we have a master with multiple links to all the switches? Well, we can't, because then we will end up taking up the ports of all the switches, and you can't make a big enough network. And you cannot always assign only one master can be anybody, right, depending on what is being solved here. So the topology, whatever way it is, if there is a master processee, it will always result in getting data one by one from everybody else. Okay? When it does that, it's a in-cast scenario. It will take the data, it will do some operation like, MPIs, it'll do some average or whatever, it will do some mathematical operation and then share its data back. This is what is called a reduction operation. MPI all reduce. People familiar with MPI programming would know that. Okay, when master processee, because it has to do this particular thing, because it has to take data one by one, okay, it forms kind of a bottleneck. Because if a cluster, now imagine a cluster which is 1,000 nodes running a single job, the master needs to take data 999 times. Like, it will take data from one, it will take data from two, and so on. So it will take 999 individual send receive steps, okay, before it has collected data from everybody, and then it will be able to do the particular operation. And once the operation is done, it can maybe share the data in a single step, because there is something called multicasting or broadcasting, right? The data is a single number, the result is a single number, which can be sent as a broadcast packet to everyone. But collecting the data is an n-step process if you have a n-node cluster. What today's networks start doing is, we've made it intelligent so that we actually use the networking elements to also take part into computation which are not standard mathematical computation, but computation which are network oriented computation. Like when you're trying to run that reduction operation, the switches or network switches themselves can actually collect data in a single step from all the connected slaves and do a reduction. Reduction can be as simple as doing a sum or a minima or a local minima maxima, or doing an XOR or AND operation, depending on whatever application demands. Okay, so now that you look at it, every switch in the network can take data in a single step, because all the servers which are connected to it are connected in a parallel manner, right? So in a single step, it will be able to receive data from n, 20 servers, or n number of servers, where now n is equal to the number of servers connected to that switch. Every switch will do it in a single step. It will do the operation and then send the result to the next level of switch. Okay, so now you see we reduced a n-step operation to a two-step operation. Two-step for a network size and a topology which is two levels of fat tree. Okay? This is one of the advancements in networking, where we start integrating compute elements so that high performance codes can be accelerated by offloading certain things into the network itself. Okay, and because you're able to do it in two steps, the top level switch is able to now share the aggregated result in a single go, but all the lower level switches can collect the data in less number of steps. And therefore, and by the way, if you look at practical application, I'm giving you a simple profile of a weather application called WRF. Okay? WRF is a weather application which is used for weather prediction and forecasting. It takes huge amounts of input data, it distributes it to multiple servers. All the servers now, they need to talk to each other, and these are the various calls that they're doing. They are, MPI wait refers to the servers waiting for everybody to finish. Like, they have to synchronize, right? When everybody is doing their job, one rogue person cannot keep doing whatever it wants. There has to be some synchronization step where everybody will come to their state, take the new data, and then start the next iteration. Then when everybody's completed the next iteration, it will again wait and then start the next one. So there are calls made in the system called MPI wait. You need to do reduction, which I talked about. You need to do some broadcast. You need to do some point to point. You need to do all reduce. So you need to do lots of communication operation. I just want to show you one particular operation which is there in this dark green and which is there in this brown. Okay, it is all reduce. Okay? You see that in a particular runtime, almost 20% of the time was spent in doing a reduction. And also for wait is one of the main thing, because most of the jobs are wanting to be run synchronous. Compute and communication has to synchronize, but you see there are collectives as well. So there was so much of broadcast, the blue part. There was so much of all reduction, and the reduction was only 4 byte and 8 byte, if you see this green line over here. And okay, so if we are able to do this particular portion inside the network, we will actually reduce this 20% to less than 2%. And therefore network has actually helped in accelerating the compute. So it's an intelligent network. Okay, it is not doing only packet passing. This is one of the things. So just to give you some examples, MPI all reduce performance for a particular message size. If you look at small message size, you look at it as software versus hardware. When I say the dark green line, which is standard InfiniBand, versus the light green, which is InfiniBand with sharp. If for a certain message size I took 400 microsecond to complete an operation, with in-network computing enabled or with intelligent networks, I'm able to do it in around 60 microseconds. Generally, we are able to reduce 10 times the time spent on doing these kind of communication with intelligent networks. And this whole thing also is required for AI performance. Why? Because think about a simple image recognition, right? Whenever you do any training, forget image recognition. Let's talk about simple training applications, right? Whenever you do any training application, what does it do? I mean, what does the neural network do? It actually takes in data. There is a parameter server which actually looks at, in every iterative step, it looks at all the data, input data, and tries to train itself by getting a new weight. Okay, tries to assign a weight, and this weight, the new weight, is a calculation done by collecting data from everybody, the delta from everybody, and then calculating a new weight factor and then distributing the new weight factor. Then again, the next training cycle starts, where every training agent will again give its own delta weight to a parameter server, and then the parameter server will do some operation and again try to fine tune. So this is again the same kind of operation that I talked about earlier, right? And therefore it can also be mapped into network acceleration, which is what is done by the current intelligent networks today as well. So one thing is, so that is one technology, let's say. Okay, how do we apply it? So to apply it, let me go into a little bit of details of a computer architecture, a current GPU accelerated computer architecture. You all are aware of standard GPUs. You must have seen, I'm showing a current generation today's NVIDIA A100 GPU. It has certain amount of teraflops for floating point 64 performance. It has got certain amount of connectivity. You can see here different interconnects so that multi GPU can communicate to each other and solve a job. And therefore, this GPU is then put into a motherboard. Multiple of them are put into a motherboard to form a GPU accelerated system. All these GPUs are connected to each other using very high speed interconnect, and they exchange data between each other. Okay. When you want to go out of a server, what if you need more than 8 GPUs for your training workload? There are clusters right now, if you look at top 500, which have got thousands of GPUs doing a single job. Okay? So you need to go out of that 8 GPU. So here we have connected those 8 GPU in a single motherboard. But if I want to go out, then I need to have those network cards. This is what I show in this picture. There are multiple network cards over here, right? They also connect onto the motherboard. and it forms a full GPU accelerated system. This is one particular building block of a particular supercomputer, right? So many GPUs on it, so many network cards on it. And this is how it looks like. If you look at the logical connection of various elements, it contains the processor, it contains some PCI Express switches. You would have seen any standard PC, there is a PCI card, right? How do peripherals connect into a server? There are PCI cards. PCI cards are put into slots which have their electrical signals coming from a PCI switch. Okay, so, but I want to create a cluster which is bigger than this. Okay, then I will connect multiple of these systems onto a single cluster. And again, I give you an example of that standard factory topology. Okay, what I do here is, as you can see, oops, then I should be able to show my pointer as well. Yes. So what I do here is I take a GPU node with multiple GPUs inside, which has got multiple network cards to exchange data outside, and I connect it to multiple switches. Okay? And all these switches are in turn connected to another layer of switches so that every node can talk to every other node without any blocking. Okay, when I have connected all these nodes in this particular manner, I form communication rings between the various GPUs inside the servers. When I form these communication rings, I am able to do those reduction operations that I talked about within the domain of these rings. So my switches can actually contribute to doing calculations of an AI workload as well. Okay? And that's the reason. And the reason I have connected my servers in this particular manner is to make use of the technology that I talked about earlier. So when you look at, so the whole point of this talk was design principles for high performance compute, right? High performance clusters. This is one of the design principles. You don't, when you create a large supercomputing cluster or a large AI or a machine learning cluster, you don't randomly go and connect anything anywhere. Why? Because you need to exploit all the benefits of the technologies that are present in high performance networks. And for doing that, you need to look at the internal architecture and connect it in a certain way. And when I say you need to do it, I'm not saying that every user needs to look into it, but every user should be aware of it. Finally, when it comes and gets deployed from a particular company or a particular institute, most of these things are taken care of. But when the user understands in depth of why it is connected like this, what maps to what, then when you do your parallel programming, you will try to pin things properly. You will try to pin the buffer of GPU1 to the adapter one, or the data transfer that has to happen from the buffer of GPU1 should go from the adapter number one. Okay? Again, it is all taken care of by the internal libraries that are built in, but those libraries are configurable, right? There can be systems which is like what I showed you right now, but there can be systems which might have a different kind of architecture. So to be able to tune the libraries, okay, so that the distribution of data and so that the distribution of buffers is done in such a manner that it can actually make use of the entire system with all the advanced technologies is uh, is the holy grail over here, right? So this is one thing. Again, what all does it give you? So I'm just showing you again the reduction bandwidth. If you were using nickel library, let's say you're doing CUDA, you have collective communication library from NVIDIA, it is nickel. If nickel was running as software, you would get a certain amount of bandwidth. As soon as you were able to do offload of many of the processes onto the switching element, you would almost double the bandwidth. Okay, so and that's the reason. Okay, this what I'm showing is, this is actually the topology of one of the largest clusters that NVIDIA has, or one of the top, and it is also the topology of many of the largest supercomputing clusters in the top 500 list. It is connected in this manner, what we talked about. You have got these compute nodes at the bottom, which do a crisscross connection into a group of leaf switches, which do a crisscross connection into a group of spine. The number of crisscross connections versus the group number of switches in a group is all defined by what would be the most optimal way of offloading the collective operation. And then, because it is such a large cluster, you need a third level of switching as well. Again, this is an example of a fat tree topology, a 3-tier or a 3-level fat tree topology. So the reason these clusters are made like this is because of all the things that we talked about till now.